Hi, I'm Jack Baker, and this is some bonus material from my CEE 203 class, Probabilistic Methods in Civil and Environmental Engineering. I'm going to provide a little bit of extra material on set theory and probability theory, going a little slower than I did in class. Okay, so we talked about set theory. So we're defining the sample space as the set of all possible outcomes in an experiment. So in our Venn diagram over on the right, that's the rectangle. And anything that can happen from the experiment is somewhere inside of the rectangle. If we think about the example I've got in the lower right of the roll of a six-sided die, the sample space would be the number that we get out of that roll, a 1, 2, 3, 4, 5, and 6. That's the total sample space. And we denote that as S. Then any subset of that sample space, we would call that an event. And an event, if it doesn't include the entire sample space, and an event may or may not happen when we have an experiment. So in my example of the roll of the die in the lower right, we can think about an event that we get an even number, right? So the even number outcomes are a subset of the sample space, and the outcomes of 2, 4, and 6 would be outcomes that are in the event, and the other outcomes of 1, 3, and 5 are not in the event. So that's a subset of the sample space. And we'll denote that with an E. When there's more than one E, more than one event, we can give them separate names, or we can call them E1 and E2 and E3 and so on. Another event in the example is the event that we get a number less than 4. So the outcomes would be 1, 2, and 3. And in our Venn diagram, we'll oftentimes draw some sort of subset of the sample space, oftentimes a circle, and then we can label with a letter inside of that circle to denote which event that is. So our E1 and E2 in the Venn diagram, we could denote as circles inside of the diagram containing part of the sample space. Then oftentimes we want to do operations on those events and do some sort of manipulation of the outcomes in those events. And the union and the intersection are the most common operations. So a union of events, we'll read that as E1 and E2. And that contains all outcomes in either event E1 or in event E2. So we'll use this U notation to denote a union. And so the union of E1 and E2 we can denote in the Venn diagram. I'll hatch that in red, is kind of any outcome that's in either E1 or E2. So all of this red hatched area would be the union of E1 and E2. So in our example of the roll of the six-sided die, if we think about the union of E1 and E2, we've got 1, 2, and 3 in event E2. And additionally, we have 4 and 6 as outcomes that are in E1. So the union would be 1, 2, 3, 4, and 6. The other operation we can do is an intersection, and we'll read that. So we need the outcomes that are in both E1 and they're also in E2. So we'll use an upside down cup for the notation, or more frequently we'll just write E1 and E2 adjacently with nothing in between. So here we need the outcome to be in E1 and also to be in E2. So it's not the collection of all possible outcomes, it's only the outcomes that are in both. So in our Venn diagram, we can denote that in some alternate color, and this would be just the overlapping region between E1 and E2. So that would be the intersection of E1 and E2. And in the six-sided die example with the E1 and the E2, the only outcome that's in common between E1 and E2 is the outcome of 2. So the intersection would just be 2. Okay, we can take those manipulations a little further. In particular, when there's 3 events, things get a little more interesting. So here's some operation rules. The first thing to note is that there's no ordering to these operations. So the union of E1 and E2 is the same thing as the union of E2 and E1. Right? That's because in the definition of the unions or intersections, there's nothing different between the first term and the second term in that definition. All right. If we do, there's also no ordering if we're doing just unions and intersections. So if I do the union of E1 with E2 with E3, it doesn't matter whether I do the union of E2 and E3 first and then E1, or E1 and E2 first and then E3, or so on. There's no ordering in that operation as well. The distribution is a little bit more interesting. So if we do some parentheses around the union here in this E2 and E3 case to enforce that we do the union first and then we intersect it with E1. let's do that in the top right Venn diagram here. We can denote that. So the E2, E3 union is going to be the events that are in E2 or in E3. So let's hatch that. Okay, and then I'll denote what that is. So that's E2 union E3. So if I want the intersection of that hatched region with E1, let's use a highlighter to mark that. So that'll be the intersection. It's got to be inside of E1 and it's got to be hatched. So it'd be that region right here. Okay. Let's denote that. So that's E1 intersected with the union of E2 and E3. Okay. Now let's try the right-hand side in the lower figure. So first we'll take the intersection of E1 and E2. We'll hatch that. Then we'll take the intersection of E1 and E3. Hatch that in red. And then if we take the union of those two, that's going to be anything that's hatched in any color. We can highlight that. And we'll see we've got the same highlighted region in both figures. So we can see that those will be equivalent in terms of the outcomes that come out of that. Okay, so we've got this distribution type property. And the yeah, I think that's good. Let's talk about one more case. So if we don't have parentheses in there, we need to think about an order of operations. And in terms of order of operations, intersection takes precedent over union. So here, let's do a couple more Venn diagram calculations. So we've got the E1, E2, and E1, E3. And if we take the union of those, that's the calculation we did on the previous slide in the bottom. And then if we compare that to the right-hand side where we do the operations in a slightly different order. So here with the parentheses, we'll do the union first. So the union of E1 and E2 will be this red hatched region. Okay. And then if we take maybe let's go to the front. If we take the intersection of that with E1, so it's going to be everything in the red hatched region that's also in E1. So everything in E1 is in both. So I guess let's denote that in blue. Okay. And then finally, we'll take that blue hatched region, which let's label it even. So this is E1 intersected with E2 union E1. So then we'll take that whole thing and we'll take the intersection with E3. So that's going to be everything that's in the blue hatched region and also in E3. And actually, let's do that with the highlighter. So that's going to be only this area right here. So the highlighter region is E1 intersected with the union of E2 and E1 intersected with E3. And we can see that on the right-hand side and left-hand side Venn diagrams, the yellow shaded regions are not equivalent. So these two operations in the mathematical equation are not equal. So there is a need for doing order of operations. We have to do the intersections first and then do the unions second. And with this slide and the previous slide, right, the mental structure that I put to this is that unions are kind of equivalent in their order of operations and association and distribution things with addition. And intersections are equivalent to multiplication. So in terms of this order of operations, when we say intersection takes precedent over union, we could change that sentence to say multiplication takes precedent over addition, and that's exactly the order of operations we do when we do algebra. Similarly, on the previous slide, the commutation, the association, and the distribution laws, those all hold if we think about multiplication and addition as being the operations instead of intersections and unions. Okay? So that gives us a set of manipulations we can do with these operations, and it gives us some rules for how to do the order of operations. Finally, let's talk about operations once there are complements in here. So, and we don't have it in these slides, but I talked about it in class, that the complement of E1, which will denote E1 with a bar over it, is all events that are not in the event E1, or all outcomes that are not, let's call it outcomes. All outcomes that are not in the event E1. So an outcome is either in E1 or it's not in E1. And sometimes it's easier to just define an event as the complement of some other event. Okay? And so when we do these complements with these overbars, that's another operation, and we have to think through how that interacts with intersections and unions. So let's do a couple calculations. I'll do some shorter ones. So if we take the union of E1 and E2, let's hatch that in red. Okay, so we've got the intersection E1, E2, the union of E1 and E2. And then when we think about the overbar, we're going to take everything that's not in E1 and E2. So let me highlight that. And let's label that. So this is the complement of E1 union E2. And on the right-hand side, we've got an equivalent term, which is not immediately intuitive probably to you if you haven't seen it before. So let's take a look at this one. So the first term here is the complement of E1, and notice there's a break in the line, so that the complements are applying to the events individually, not collectively. So we'll do the complement of E1. Then next, we'll do the complement of E2. So everything not in E2. And then when we take the intersection of those two complements, that will give us this thing that we're interested in. So let's highlight that. So we're going to highlight only the part that's double hatched, right? So that means it's both in the complement of E1 and the complement of E2. Okay. And we see that those two those two highlighted regions are identical. So we've got an equivalent operation. Okay. And the warning here is just be careful about putting complements on the top of operations, because the complements interact with these intersections and unions in somewhat non-intuitive ways. And these rules are called De Morgan's laws. For the top one, you can see the second equation here indicates that this is extensible to more than two events, and things will still hold. Okay, so let's move to the bottom figure, and let's show the equivalence of these two. So the first thing we'll do is take the intersection of E1 and E2, and then we'll take the complement of that intersection. So everything that's not hatched. Okay, and then on the right-hand side, let's try this one. We'll take the complement of E1. So everything that's not in E1. Then we'll take the complement of E2, everything that's not in E2. So we'll hatch everything except that circle. And then we're going to take the union of those two complements. So we're going to take everything that's not in E1 or not in E2. So everything with any kind of hatching in it gets counted. So the only thing that doesn't have hatching in it is that little slice in the middle of the figure. Everything else has got hatching of one color or another. Okay, and we see that the two shaded regions again are equivalent from the left to the right. There we can see some kind of basic indication that these De Morgan's laws hold. Again, that second set of terms has an extension to more than two events. And these operations, these equations on the left always hold, so we can just work with those mathematically. But if we ever get in trouble in terms of our intuition or trying to figure out what's going on, you can always go to a Venn diagram like we have on the right-hand side to double check that everything's working, or that you're not making up some rule accidentally that's not actually a rule. So I like to use those Venn diagrams for some intuition building, but in a more basic kind of calculation sense, we don't need the Venn diagrams. We can just do the operations themselves. Okay, so that's a little more careful look at a few items from class, and I hope that's a helpful review for some of you.